All right. Let me just go over that briefly again. We have 10-volt voltage source connected to two conductors that are in series. They have different conductivities. Let's say they have the same surface, or not surface, the cross-sectional area. Let's say that segment one has twice the conductivity of the second one, and also the length, uh, two times the length of segment two. And let's say that this part of the problem is asking what is the ratio of the electric field in segment two to that in segment one? So, okay, we're working with conductivity. So let's see if we can use the microscopic form of Ohm's law, right? In that case, current density is equal to the product between the conductivity and the electric field. And this equation, it you see it as a vector equation, but for our sake, because we're getting asked a ratio between E2 and E1, what we're going to divide vectors by each other. And you can't really do that. So we can just use the magnitude form. It says that same thing, just taking the magnitudes of each. Okay, it's asking the ratio of the electric field in segment one to that of segment two. So we can use this form of Ohm's law, this microscopic form of Ohm's law, to create an expression for electric field so that we can later divide them. So, okay, we can just divide both sides of this equation by sigma so that we end up with E being equal to J divided by sigma. But we also know, and this should be on the formula sheet, we also know that current density, just by definition, is equal to the current going through a wire and the wire's cross-sectional area. So we can combine these two equations. We can substitute this J for this I over A and end up with E being equal to the field being equivalent to current divided by um, sigma times area. Okay, now let's apply it to the first segment. Say E1 would be equal to, respectively, I1 divided by sigma 1, A1, right? But look at this. These are two components, we can call them, I guess, two components connected in series, which means that the current going through them has to be the same. So we can say right here that, okay, I1 equals I2 equals, as a generalization, I. And this is what goes through both segments. So we can say that E1 is equal to I divided by, um, we have this conductivity constant, omega 1, divided by, again, or multiplied with the cross-sectional area that is universal to both segments. And, okay, like I stated earlier, the conductivity of segment 1 is twice of the conductivity of segment 2. So let's just choose sigma 2 to make everything in terms of. This will be convenient a couple of steps down the line. So what we get from this via substitution is this is equal to 2 sigma 2. So 2 sigma 2 times A. And okay, now let's create a similar expression with, because it's, maybe it won't be the same, maybe it will, but let's create the same kind of expression for the second segment in terms of uh, this specific conductivity. So E2 would be equal to I2 over sigma 2 A2, again with the generalizations that I earlier defined. Uh, we can just leave this because this is the variable we want things in terms of. And yeah, we just put A there. And notice, given each expression, E2 is equal to 2 times EI. Because look, this has a 2 in the denominator and it's identical to this one, except for that 2 in the denominator. So E1 is equal to half of E2. So we have this equation right here, and it's asking us for this specific ratio, E2 over E1, in which case, you have 2 times E1 divided by E1, and the ratio ends up equivalent to 2. 2 is the answer for this part. And okay, before I go any further in this problem, because there's a second part that I want to go over with you guys. Um, any questions about how I got this answer so far? Any steps that might be in need of clarification? How does everybody feel about this so far? Okay. All right, perfect. So again, stop me if you feel like you need some clarification on anything, but I'm going to go into the second part of the problem. So let's say B is asking us, uh, let's say, what is the ratio of the resistance of segment 2 to that of segment 1? So essentially, it's asking us, let me move this up a little bit. What is R2 divided by R1? So here is another equation that is either going to be on the formula sheet or you can derive it using basic formulas on the formula sheet. But here we have that an equation that tells us, and remember this because it'll save your life on the test. We have this equation that says that the resistance of a wire is equal to its length divided by its conductivity times area. And okay, one thing that's going to help us in this problem is that detail that I mentioned earlier, in which um, the length of the first segment is twice the length of the second segment. And okay, now I guess we can just go ahead and start applying this equation to each of the segments. So let's say R1 is equal to L1 over the first conductivity times A1, and then, like I said, let's do the same thing just for the sake of consistency. Let's put everything in terms of L2. So L1 is equal to 2 times L2. So we just substitute that up here. And the first conductivity is 2 times the second conductivity, the conductivity of the second segment. So this would be 2 sigma 2 times the area. And okay, let's do that for the second one. We have R2 equals this, and this. And okay, everything's in terms of L2 and sigma 2, so the A doesn't need a subscript. So we can put it in this way, and oh, these two's cancel out. So You end up with L2 over sigma 2 times A. And look at this. These are the same thing. So when it's asking us for the ratio between them, we're just going to get 1. Any questions before I go on to the second problem? Does this seem straightforward? I'd say this second part is pretty similar to how you solve this first part. Yeah, put SI units on as much as you can on this test. That's just one universal that I've noticed with pretty much every question asked. Just in any of the problems that I've done, even in recitation. How does everyone feel about me jumping to the second question? Everybody ready for that, or should I clarify anything? Okay, perfect. Second problem. Okay, let's say that we have a voltage source. Let's say that it is 9 volts. And here's a point A in the circuit, a point B in the circuit. There's a switch that makes contact with B. It flips at t equals 0. And okay, let's say that until we flip this switch, the voltage source is connected to this 4 microfarad capacitor. And here's this resistor, say 25 ohms. All right, so it's, let's say, what should we look for in this problem? Oh, let me write this here. 2. What is the current that is going through the resistor? What is the current going through the resistor after 50 microseconds? So let's say I is a function of t, and what will we get after plugging this into the function? So, okay, let's see. We have this current decay formula on the formula sheet that I can go over the derivation for that. There we'll get into differential equations, but I will say for the sake of this test, just know how to use it more than deriving it. But if you can derive it, you know that's pretty good. It's good that you understand it. But for the sake of this problem, I'm just gonna go ahead and use it. So let's say function for current in terms of time is equal to the initial current times this exponential, and let's say that the voltage of the capacitor, we know that the voltage of the capacitor um, at time equals 0 as soon as we flip the switch is equal to 9 volts. Let's say the 9-volt battery has been charging it for a good amount of time. So once we flip the switch, the first voltage drop that we can ever measure across this, let's say it's 9 volts, right? And we know that the initial current going through this circuit, because now at time t we flip the switch, let's say, we can use Ohm's law for that. So we get the initial voltage divided by the resistance of this capacitor, or this resistor. And okay, we have the same exponential here. We can pretty much just plug 50 microseconds into this t value here. That's really what you do for this problem. If they ask you a problem for this, it might look too good to be true, but there will be problems where you really just take a formula from the sheet and plug in some numbers. It's one thing I've noticed even with the past exam and some homework problems. So okay, let's say I of 50 microseconds. Someone asked earlier about SI units. Yeah, like I said, as early as we can, it's better to just convert everything to SI units because it makes solving this way less painful. So we have I of 50 times 10 to the negative 6 seconds, right? And now we can just plug stuff in given this expression. So we have the initial voltage, uh, which I said to be 9 volts. So we have 9 volts divided by the resistance of the resistor. So we have 25 amps, or it's 25 ohms, excuse me. And then the exponential, the time we're plugging into this is TS negative here. So negative 50 times 10 to the negative 6 seconds. And the resistance is 25 ohms times the capacitance, which is 4 times 10 to the negative 6 farads, microfarads. And okay, let's plug everything in. Okay, this is what I got for that problem. Can someone confirm for me if this is what you got as well? Okay, you got exactly this. Okay, perfect. All right, so this one shouldn't be too hard, but of course, if there are any questions before I go into the next one, please let me know. We good with this
What?
one so far?
Sorry, I have a quick question. I have it
Oh
written
yeah,
for the decay that that it's negative for the current initial. Because
where does it?
isn't this the same as the charging formula? Is it the same for charging and discharging for the current?
Yeah,
Okay.
yeah, because the yeah, because charges, you take the derivative of charge and you get current, so you can, yeah, pretty much turn one equation into the other one. But why should this be negative?
No, I think I may have just had it written down wrong.
Oh no, no, okay, yeah, you're good. Does this make sense though? Everything I did so far. Oh, and forgot to write down what I got. Everybody good with this so far? All right, all right, perfect. Okay, I'm gonna go on to the next one. So problem number 3. Okay, I know they they're most likely gonna have a Kirchhoff problem on the test. So you have different loops, and you'll see what I'm about to draw. So let's say you have a voltage source here, a resistor, and let's say this is loop 1. There's another loop, connected to that. You have a resistor here, let's say 10 amps, oops, 10 uh, ohms. And right here you have, let's say 20 volts. So this would be negative, this would be positive. This is 20 volts, negative, positive. So make sure to study Kirchhoff's law as well, because you'll most likely see a circuit like this with different loops. And let's say it's gonna ask you something like, okay, let's say there's, you see this branch right here. It's kind of, okay, yeah, that's a little easier to see. There's this branch right here, and what is the current going through it? What is the magnitude of the current in the middle branch of the circuit? So let me just write that here. Current in middle branch.
If there is a question with loops, will they be drawn on the diagram on the test, or we have to draw them ourselves?
What do you mean? Like the circuit itself, or this that I drew here?
The little loop symbols.
Oh, they won't have that on the test, but I mean maybe they could have it if you're lucky, but it's not too unlikely. But if they don't have it, then let's say there are you can define a loop to go in this way for this part of the circuit, and for this one you could define it to go either way, right? You can say that the current for loop 2 goes that way, but for the sake of consistency, I'm making them go kind of in the same clockwise direction, as long as it's consistent with the rest of what you do, or as as long as the rest of what you do is consistent with the directions that you set for these currents in the loops.
Do we need the resistance for the top resistor?
Oh, I forgot to give that. My bad. Yeah, that's yeah. For the sake of simplicity, we can say that they're both equivalent in resistance. So let's say we want to find the current in the middle branch. Um, okay, so using Kirchhoff's law, let's divide the problem into loop 1 and loop 2. All right, so we can start from here in the loop. We want to add up all of the voltages, and all of those voltages, as part of Kirchhoff's law, should equate to 0 when you add them all together. So, okay, you see this source right here? We're going clockwise. That's what we defined earlier. We are starting on the negative side of the battery. So that is how we will write down that voltage. Negative 10 volts. And okay, what goes through this resistor? What is the voltage drop across this resistor? Well, let's say we don't know the current yet going through that loop, but we can just leave it here as a placeholder, times 10 ohms. And okay, there's nothing more in that loop. So you add these up, you should get 0. You have to get 0. That's Kirchhoff's law. And okay, now we can just solve for this current in the loop, in the loop that we're currently solving for. And okay, this negative 10, you can bring it to the other side and it becomes positive 10. So I1 times 10 ohms is equal to 10 volts, which means that these 10s cancel out. So this I1 should be equal to 1 amp. Right? Does that make sense to everyone? What I'm doing with the, just as I'm adding all of these voltages. Okay, perfect. Without much being said, you can do the same thing for loop 2. So let's say you start here, and we're going this way, clockwise. So we start from, oh, look, the negative side of the 20 volts again. So negative 20, oops, negative 20 volts plus the current going through loop 2, going through the 10 ohm resistor, and there's nothing else. So these two should add up to be 0. In which case, you can move this negative 20 to this side. You have I2 times 10 ohms equals 20 volts. And from that, you should get, you divide 10 by both sides, or divide both sides by 10, and you end up with I2 equals, I would just write it here, 20 volts over 10 amps, or 10 ohms, and you should get 2 amps. And okay, the current of the middle branch. So check this out. I guess I can draw it up here. If we're talking about the middle branch, I1 is going to point this way, because we're going clockwise. And I2 should go, since it's going clockwise as well, the current should go this way. So since we have two currents, we just add them up. And since they're going in opposite directions, then one is going to subtract from the other. So if you want to find the current, and to find the current in the branch, you just take I2 and add I1 to it. And okay, we can say, wait, hold on a second. Let me make sure of something. No, excuse me. No. Sorry. One little detail I messed up. No, you subtract them from each other. It is asking about the magnitudes of the currents. It's the magnitude of this current at the end. So since they're going opposite to each other along the same line, we can just subtract the magnitudes from them. So I2 minus I1 would get you 2 amps minus 1 amp, in which case you just end up with 1 amp, and that would be the answer for this problem. One comment I have on this particular problem is the most important thing to know to solve this problem is what I'm doing in each loop. These are, I don't know what Dr. Aktash or Leila call these, but these are KVL equations. This stands for Kirchhoff voltage loop. But if you can't do these, that would be the worst thing for this kind of problem. So I would suggest studying closely these KVLs. But with that being said, does this make sense to everybody so far? Or anything I should clarify?
Do you have to start on the negative side of the battery, or did you just choose to do that?
I could have started, let's say for loop 2, I could have started right here. You can start from any point, as long as you return back to that same point as you're going through the loop. If you start here and then, okay, count clockwise, so we're going this way, we just end up, we start from that negative side. If it was like positive then negative, then in that case, that would have been the 20 volts that we put here would have been positive. If that answers your question.
Yeah, thank you.
Yeah, no problem. So, okay, should I go on to the fourth problem that I sent to you guys in my PDF? All right. Like I said, feel free to stop me. Don't feel bad for interrupting, as long as I'm not going too fast. So, problem number 4. In the PDF that I sent to you guys, there's, okay, let me just draw this out. There's this kind of semi-arc shape, right? And this is a loop. These lines are wires, right? And the current going through this loop is 5 amps. And okay, we have this central point, we call it P, and from the outer edge to that point, the distance is 2 centimeters. And we have this inner radius where that would be 1 centimeter, right? So, given this, let's say we want to find an expression for the magnetic field at this point. What is the magnitude and direction for the magnetic field at point P? So, okay. One thing we can do is, since we have these continuous curves, we can think to, okay, what along this piece, what effect does that have on this point? What is the magnetic field strength at this point P because of this increment, right? This incremental piece of the wire. So what we can do is we can use the Biot-Savart law, and we can say, okay, a piece of that magnetic field, or the magnetic field induced here at this point from this piece of the wire, is equal to, you have these constants, and this is on the formula sheet, if I'm not mistaken. Let me confirm that. Yeah. This is on the formula sheet. So you have current times this length vector. This is an arc length vector, or the sorry, the direction. Let's say we're like, we have a line here and it's going this way. That is what a DL would look like, just clarifying the intuition behind that increment. And okay, we have the cross product between this and radial distance as a vector. And well, if we're going from the formula sheet, this would be a unit vector, and this at the bottom would be r squared, the magnitude squared of this vector. But given the definition of unit vectors, this is just the vector divided by its own magnitude. So we can rewrite this whole thing as, we keep all of this the same, I dl vector cross, we have, instead of r hat, just, the r vector divided by r squared, and the magnitude of this, so that squared turns into cube. And we can say that, okay, these would stay the same. We can say that the field is, let's do the magnitudes now and just figure out direction later. For going off of magnitudes, we'll get that we can multiply this current by the magnitude of this vector by the magnitude of this vector times the sine of the angle in between these two vectors. But here we have a radial vector, and we have an arc length vector, which means that, and this R3 goes at the bottom, let me not forget that. That means that, okay, let's say this is r. ds is always going to be, or not ds, dl is always going to be tangent to this circular arc. So just given the geometry of this loop, at every point the radial vectors are always going to be perpendicular to the arc length vectors. So we can say that this will be 90. So this whole sine function will just go to 1. So we can reduce this equation to this form. Divided by r cubed, and then these cancel out. You'll end up with this. Okay. Now we only have an increment of the magnetic field strength at this point. And if we add up a bunch of increments, we know that we get the total magnetic field at this point. In which case, we can express the magnetic field strength to be the following integral. We have dB, so we just put everything here within the integral. And okay, what can we do now? So all of these things are constant along the arc length. We can just pull them outside of the integral, in which case we'll end up with this. Yeah. And here we have again the arc length increment, but because we're dealing with circular. Oh, sorry, I just now saw this question. Will both r values in the equation normally represent the same radius value? So right now I'm creating a general equation because you have these two circular arcs, these two paths that are geometrically similar. They're just scaled. So I will plug in these respective radii later. So no, we don't use the same r for them. But in the sake of for the sake of generality, we're just creating this general equation. Yeah, this r just it pertains to it. It refers to one arc at a time. So for just some arbitrary arc with radius r, this equation would be true. Does that answer the question sufficiently? Yeah, that's exactly what I did right here. So, um, oh wait, no, that's what I did here. So you have this r at the top from the magnitude of the. Sorry, what was that? Because it's all talking about regular radius. Yeah. So this general equation is for each of these. I will apply it to each case individually. But yeah, this r that was at the top cancels out with one of the r's since it r cubed. So yeah, what you're saying is correct. I got that same thing, r2 at the r squared at the bottom. So with all of that being said, we have this arc length increment, but since we're dealing with a circular path, or I guess two circular paths, we can say that dl is equal to uh, radius times an incremental angle. So with that being said, we can, all of these, of course, stay the same. So I'm just gonna write these, give me a second. And now we can say that our the theta, we have our d theta within the integral in substitution of this dl. And I noticed that these, we have some r's canceling out here. So we end up with, yeah, those equations will be on the test equation sheet. It appears to me that they typed out a formula sheet and forgot that there were some formulas they should have included, so they put those in last minute handwriting, and then they scan that and send it to everyone. But yes, those will be on the test. If I'm remembering correctly, I sent everyone also a PDF of the formula sheet. So what you see on that is going to be on the test. No question about that. Yeah, no problem. Okay, going ahead with the problem. I'm just simplifying some stuff. You have this 4 pi here. R squared, you have this r that cancels out with one of these r's, so just end up with 4 pi r at the bottom. And okay, we have this integral, right, which is asking, we're taking a bunch of increments of angle. So this integral is telling us, what it's giving us is, what it's asking for is the total angle as you go specifically from here to, okay, wait, that's a little hard to see. You have this point, and imagine a point here, and you're sliding it all the way this way to draw each curve. The total change in angle will be a 180-degree angle. And for the sake of this problem, we can say, okay, we can use, let's see, we can use radians for this. Since we have this 4 pi r at the bottom, things will cancel out cleanly. So yeah, from here to here, the total angular displacement is 180 degrees. In other words, pi. So this whole thing evaluates to pi. I see something here. Since the length of the radius looks like half of a circle circumference, could I represent dl as 2 pi r over 2? Yeah, pretty much you can. I guess I'm just doing it the long way, but yeah, you can do that. So just continuing the problem, you have these things, and then the integral turns into pi, 4 pi r. These pi's cancel. So what you should get is mu over 4r, or mu I over 4r. And okay, it's asking us the magnitude and direction at point P, but look at this. We have two sources of, two arcs that will give us different BI values evaluated at this point. So pretty much we should find the difference. We should find the total, but the reason it becomes a difference is because you see that, okay, the current goes this way, and, you draw an arrow here. It should go this way respectively, and should go this way, continuing throughout the smaller arc. And you notice that when you evaluate these arcs with respect to each other, the current is opposite. So that is why you're taking the field strength from one and subtracting it from the other. In which case, let's say the magnetic field strength at point B is equal to oops, b2 minus b1, right? In which case, we'll have this formula we came up with for b, just evaluated for the b2. This, I guess I can. Oh yeah, let me be more specific. This is one. This is two, and this is one. Circular arc two, and then circular arc one, more specifically. So yeah, we're using this general equation, applying it to each individually. So for the second one, we have let's see, 4 times r1 or r2, excuse me, minus the same thing, but for the second arc or the other arc b1. So we have 4r1, and okay, we can factor some things out since there are some constants like mu and 4 and I doesn't change, so that's always going to be 5 amps in this loop. So we can just factor all of this out, and then we get 1 over r2 minus 1 over r1. And I guess now we can just plug in some numbers. So we have 4 pi times, what's a crazy looking pi, times 10 to the power of negative 7. The current is 5 amps, divided by 4. Oh, hold on. So are they subtracting because they are opposite currents? Yeah. You're adding them, but that addition turns into subtraction because one of them is negative. Because now you just these are so imagine you're integrating over this whole path, but these don't count because you'll have the magnetic field strength induced by these parts would be 0, just because of how they're positioned with point P angularly. So continuing with the problem, just plugging in some numbers. This is what you get in front of the parentheses, and then you have 1 over R2 is equal to 2 centimeters. So that's 0.02 meters minus 1 over 0.01 meters for the 1 centimeter radius. And okay, now we can just plug these numbers in. What I got for this problem was, or just now, is negative 7.85 times 10 to the negative 5. And look at this. Notice how we get a negative value? And it turns out that we subtracted the bigger magnetic field strength from the smaller one, but we're just looking for the magnitude, and magnitude is never negative. So we could just subtract the other one from the other one. So we have 1 over r1 minus 1 over r2. We can just flip the whole thing, and it will give us the same value. Magnitude wise. And then here we put the 0.02. And for that, we should get a positive value for the pretty much the total magnetic field strength at point B. Anybody have any questions so far? I know that problem was a little longer than the other one. Oh, what the?
Yeah, I had a quick question.
Yeah.
So, for all the math we did up until we plugged in the numbers, is it gonna vary between like different problems, like of the same problem, but like if like the numbers are different or anything? Because it's just derived from the equation sheet, right?
Sorry, what exactly are you asking?
So sorry. So is the process we did before plugging it in gonna change like
Oh,
between problems, or is it gonna be the same for every problem of this like
the
math?
problem, well, since these sub parts of the bigger problem have the same geometry, uh, that is why I apply the same equation to both. The geometry really depends, or really determines what the formula, the general formula, will look like later on in the problem.
Gotcha. Thank you.
Yeah, yeah. Does that clarify everything?
Yeah.
Okay. Um, I'm glad. Does this clarify anything else from anyone that needs to be clarified? Okay, I see a question. What's the direction? It's going towards P, right? Oh, yeah. Let me not forget about that. So we found the magnitude of um the of B at P, but yeah, now for the direction. So let's see. I'm just taking a look at these real quick. So this cross product right here, you have arc length crossed with the radius. So okay, you just rewrite that. Let me redraw that. And yeah, they are perpendicular. The cross product should, okay, right hand rule. Well, at least my version of it. Um, here we have DL. Here we have R. So their cross product respectively should point upwards. But notice how in the drawing, if you rotate this towards the right, towards us a little bit more, you'll see that R is here and DL is here. So you'll have to flip it for R and DL to be in their respective positions. So instead of pointing straight at us, that vector should point away from us into the page. And okay, when we're considering vectors for this problem, when we look at the total vector at point P, okay, like I said, the magnitude of, oh, I see a question. I'll get to that question in a second, but like I said, this arc, each piece of this curve is individually inducing a magnetic field with a direction and magnitude at point B. So at that point, we just add up what we get from this piece and from this piece. So, okay, for this should be the case for each curve because actually no, because okay, yeah. DL points this way, and if we continue along the curve, DL should now point this way. So now the question is, because now we have opposite directions, we're gonna have from one the vector pointing into the page, and for the other, the vector will be pointing out of the page towards us. So it really just depends on which has a bigger magnitude. In which case, this one was R1, this one was R2. Here you're dividing by a smaller number, so R1 should have the stronger magnitude, which means that it's going to be pointing more towards us than into the page. So that is what we should get. Yeah, this is the magnitude, and BP points into the page, or no, points at us from the page. And okay, I see the question. Let's see. Do we use right hand rule with rolling our fingers to find the magnetic fields of the wires? Rolling our fingers. What do you mean by rolling your fingers? You mean like curving them? Like you mean that right hand rule? Yeah. It just like this. Yeah. The current. This would be the current, right? Long. We have this circular path. So the current curls this way. The field should point at us. So yeah. Does that? Let's see. So we can just write into or out of the page instead of writing it in K hat. If you want to write it in K hat, which you might have some picky TAs. So worst case scenario, let's assume. Let's say that X is towards us, Y is that way, and Z is up. At that point, yeah, into the page would just mean that BP is equal to 7.85 times 10 to the power of negative 5 Teslas, I hat. You can also say that, okay, first and foremost, you write this, let's draw this view out, X, Y, and Z. If you want X to be this way, then Y will be, all the way over there into the page. So if you define the problem like this, then you can write the same constant times J hat, right? So as long as you define your coordinate frame, the XYZ axis, as long as you specify something like this for the problem early on and make the rest of the math consistent with that, you should not lose points. If that answers the question, that's a good question. I haven't really thought about that because it's kind of subjective to how you define the problem. Why is it I hat, not K hat? It would only be K hat if you're looking at it. I kind of, correct me if I'm wrong, but I think you might be looking at it like, oh, X is this way, Y is this way. So we're kind of just looking from upward, and into the page would be the Z axis. In that case, if you define it like that, you can say that this magnitude goes in front of a K hat. So like I was saying, it really just depends. That is, it would be helpful if in the test they tell us, oh, this way is X, this way is Y, this way is Z, but unfortunately, I don't think they're gonna tell us that on the test at all. They usually don't. But besides that, does anyone have any other questions about this? Does anything need to be clarified, revisited, or explained? Everyone feel good about this so far? I guess I can say this would be the longest problem you'll find on the test. If you see something like this, it's gonna be the longest one. And one comment I have, if you see this problem, know your cross products very well. I can identify 2 different points in this problem where you could mess up on what direction a cross product points and maybe mess up the whole thing. There will be partial credit, but just to be safe. Everyone feel good about this so far? Should I go into the next one? All right, well, like I said, feel free to stop me. Number 5, the last one. And this is from recitation. And like I said, this will be on the test. Don't ask me how I know that. I just know it. So, okay, number 5. You have this positive plate. And you have a negative plate. And, okay, you have this separation of 1 centimeter. So, to reduce headaches, SI units again, that'll be 0.01 meters, right? And okay, there is an electron. There's an electron going parallel in between these plates at 10 to the power of 7 meters per second. 10 to the power of 7 meters per second. And okay, what else? Okay, the voltage between these, let's say these are hooked up to a voltage source. You can draw it like this. Let's say that's 200 volts, right? Okay. Now what we want to find in this problem is what magnetic field strength and direction will allow the electron to continue as it's going parallel to these plates without deflecting into the direction of either plate, right? So one thing I would like to point out is, okay, this electron will not deflect as long as it doesn't accelerate. If it continues in the same, with a 0 acceleration and a constant velocity, then there won't be a force to pull it in any direction, because it has mass, and if it accelerates, the rest, blah, blah, blah. But at least in the y direction, we cannot have any acceleration. So, in other words, the free body diagram, for it to continue this way, will have to look like this. Well, I don't know the directions yet of the forces, but one observation I can make is if we remember that the field lines around the positively charged particle radiate outward, and for a negative particle, they radiate inward, then we can imagine between these 2 plates, positive, 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 and all of this, all of the field lines are going to go from top to bottom. They're radiating out of this top plate into the bottom plate, which is just, it's just sucking in all of those field lines, I guess you can say. So you have it going this way, and here's a fundamental equation that don't forget it, but if you forget it, it's on the formula sheet. You have the force being equal to the field, electric field, multiplied with the charge of the particle in question, and this charge holds a negative value. So that means that since the electric field points from the positive to the negative plate, given the negative charge of the particle, all of those lines will be reversed in direction. So the field, the magnetic field, or no, the electric force at all points should point upward within this gap. So, okay, we have this electric force, and this, again, this is the free body diagram of the electron. And if we want no acceleration, then that means that the magnetic force has to be equal and opposite to the electric force. It has to point in the opposite direction, and it has to have the same exact magnitude. Only that way we will have no acceleration, and this electron will stay in between the plates. So with that being said, their magnitudes, I did say this a second ago, the magnitude should be equal. And in this case, we can now start doing some magic. So we have QE equals the magnitude of the magnetic force, which is the magnitude of Q times the cross product of the velocity times the cross product of between the velocity and the magnetic field lines, or the magnetic field vector. And what we should get from this is Q times the magnitude of this vector times the magnitude of this vector times sine theta, theta being the angle in between these two vectors, right? And okay, we don't know where theta points. The problem doesn't tell us that. But what we know is when you have theta pointing, imagine a slider where you can change the value of theta, or just between these two vectors. You have v going this way, so you have a vector parallel to this bottom plate. And okay, what this sine theta becomes is a scaling factor. It literally has no other effect on it than to just scale it. So if you have an angle less than 90, then this is just gonna make this, it's gonna give you a partial magnetic force. We want a full magnetic force, so we want this sine theta to become equal to 1. What equation am I using on the equation sheet? I actually have it right here. It is this equation. Wait, hold on, where is it? Oh, here. That's the equation I'm using for, the magnetic force. It doesn't say explicitly that this is for the magnetic force, but just remember that because you have B here, it's most likely, for the magnetic force. But I promise, it is for the magnetic force. Not that it most likely is, but yeah. With that being said, you can change this value to anything, this value of theta to anything, and depending on the value, you'll either get 1 or something smaller than 1, in which case we want this sine theta to be equal to 1. so that we can get the full effect of the magnetic force. And to make this equal to 1, that means that theta would have to be equal to 90, because sine of 1 is 90, right? So if it's equal to 90, we can define it to be equal to 90. We end up with this. And Q is on both sides, so we can just cross those out, those cancel out. We end up with E equals VB. Let me put little v for velocity. Big V will be potential, right? Yeah, you have E equals VB, and we want to know B, talking about the magnetic field. So we just divide both sides by this little v. So we have B equals the electric field strength divided by the velocity. And okay, when you have two plates parallel to each other, the potential is equal to, there have been a few problems in the recitations that kind of look like this, that have the same setup. In that case, the electric field is equal to the potential between the two plates divided by the gap spacing. Okay, now we can just substitute this expression into this expression for B, this expression for E into this expression for B. We can say, because of these two relationships, B is equal to big V over little v times d. And we can solve for the magnitude now, because we know the potential, we know the velocity, we know the gap spacing. So now we just say, okay, 200 volts divided by 10 to the power of 7 meters per second times 0.01 meters, 1 centimeter. And from this, what I end up getting is, I got 2 times 10 to the negative 3 Teslas. There's a question I see right here. Is the magnetic field going into the page, and is that how we found data? No, no. So, good question. I'm glad you asked it. Just by computing this magnitude, just generally given the magnitude of how you find the magnitude of cross product, you have assigned data here, but we don't know data. The problem doesn't suggest what data should be. There's no indication, but we know that in order for us to get the full effect of this force, the cross product between these two has to be such that this sign right here turns into 1, because otherwise we're going to have sine of some theta being equal to 0.5, and it gives us half of the effect of the magnetic force, in which case we want all of it. So we know from that, okay, whatever theta should be should make this sine function equal to 1. And a good candidate for that is 90 degrees. So I'm just rolling with that. I plug 90 into the sine, and then I get QVB. Does that answer the question? It could be, 270 degrees, but all we're finding out right now is whether it's perpendicular to this velocity vector. But in a second, I'm going to determine which way it's pointing, whether into the page or out of the page. See, using the right-hand rule for this, we can use that to predict the direction of the, if we know V and we know B, but we don't really know too much in the problem yet. So that's why I'm doing it in the way that I'm doing. But your way works. We would just have to know a little more information. Does that answer the question? Does that make sense what I'm explaining? Well, I'll go ahead and you let me know if there's anything unclear with what I'm doing. Well, okay. Uh, hold that thought. Let me see what I get, and we can look at both ways of. We can try both ways. That works better. This is the last problem, and um, yeah, I have more time to go over stuff. Any questions anyone has? But 1 second. Okay, so let's say we need FB to point down. This is what I was going to say. Yeah. We need FB to point down, and given the right hand rule, if this is V, this is B, then if you take the cross product of V first and then B, you know, V going to the right or the left of the cross product, then this is where V cross B should point. But let's see. V points this way, and okay, we know that. Okay, let me just write this here. V points this way, and since FE points up, we need FB to point down. So let's say FB points down, which is, it should be V cross B. If we're just ignoring the charge just scales. We don't care about the charge right now. We just care about the direction. What would give us with respect to this vector and this cross product, which needs to point this way given the electric force direction? Should this vector be point into the page or out of the page? So let's try both. Let's say B points into the page. Let's assume that. Or let's just put a B here, B question mark. So, okay, V points this way. V cross B points this way. Oh, no. No. Actually, we need V cross B to point up. Because, yeah, Q just gives it scaling, but it also reverses the direction since it's negative. So, okay. Here, we need the magnetic force to point down. But given that, okay, back to this drawing, V goes this way, B goes this way. The cross product will go this way. But if you multiply Q with that cross product, since Q is negative, it will point down, which is what we need here. So with that being said, V cross B needs to point up, has to point upward. So we have V here. And we know that V cross B needs to point up. Correction. Forget about my previous, what I said previously. It should not point down, it should point up, given a negative on the Q. And okay, you have a vector pointing here, vector V. If B points into the page, then you just rotate, let's say, you rotate, the coordinate frame a little like more this way. And you'll have something where V is going here, B is going here, in which case their cross product would point like this, will point up. Now let's say that B goes straight at us. That's the origin. And okay, we have this coordinate frame. So B points at us. B would be here. That means V would go here. And this cross product, since B comes first and then it's V, this would point up. But if we want to, if we want to express in terms of V cross B, we're going to have to multiply a negative by this. So in other words, am I confusing with that explanation? Let me actually kind of scale it back a little bit and explain that a little more clearly. So yeah, like I said, this points into the page. So this is equal to, excuse me. Yeah. Okay, so given this, if we reverse which vector is B and which is V, the cross product would have to point downward. But this cross product points upward in the case that B is going into the page. And we need this cross product to point upward, so this has to be the direction in which B is pointing. So B points into the page, where the magnitude is equal to 2 times 10 to the negative 3 Teslas, not I, Teslas, and yeah, into the page. Does that make sense to everyone? I know at some point I kind of struggled explaining my thought process for figuring out where the B vector should point. Does anyone have any questions for what I did? Yeah, the direction for the previous problem. I can go over that. So, okay, let me pull this out. So actually, okay. So I'm gonna get to your question in a second, but someone is asking here. Can you just make Q positive? And this is for problem 5. Can you just make Q positive so you don't have to flip the direction of the electric force and magnetic force? Seems like the direction of both were flipped. Okay, so you cannot make Q positive because Q is, I'm defining Q to be the charge of an electron and the charge is negative. So you can't just, that would be an incorrect assumption that the math would be based off of. And let's see, still for problem 5. Oh, never mind. Okay. Does that answer the question though? Does that, yeah. Does that make sense of it? Yeah, pretty much just explaining it once more because, yeah, let me give a better explanation than the last few attempts. So, okay. We want these to be opposite to each other. We know nothing about the magnetic force. We just know that it should point opposite to the electric force. We know which way it points, just given where the charges are and what the charge of the electron is. This has to point that the magnetic field has to cancel out with the electric. The magnetic force has to cancel out with the electric one. So that gives us a clue of where it should point. Since Q is negative, it will reverse the product. It will reverse the direction of this cross product when we're evaluating the magnetic force. So to account for that flip, we want this cross product to point up so that Q could make it point down. And it can point upward only if B goes into the page. Because at that point, using the right hand rule, this would be V, this would be B, and if they are as such, then this is where their cross product would point upward. And yeah, it's a little weird visualizing it, I'll admit, but you just take this and you rotate it a little bit this way. You have an X, Y, Z axis here, a coordinate frame, whatever you want to call it. Just imagine you're looking at it from the side. You rotate it this way, you get this. Given the right hand rule, this is the direction in which B would have to point for us to get the cross product pointing where we would want it to point, so that Q can reverse it into the right direction as required from the problem. Just simply okay, so if you're confused about the value, I can go over that before I go to question 4 to clarify someone else's concern. But okay, here the problem requires for the electric field strength to be equal to part of this. We have a general requirement of the problem that breaks down into smaller requirements, and one of the smaller requirements is that the magnitudes will have to be equal if they're in opposite directions, so that they can cancel. So I'm evaluating each force. So for the electric force, you have QE, and for the magnetic force, you have QV cross B. And if you're taking the magnitude of that cross product, you have this Q in front, and you have the vector magnitude multiplied by sign, because it's the cross product. And if we, long story short, because I give a long explanation for this part, if this theta angle is anything but 90 or 270, then we're going to get either a value smaller than 1 for the sine of theta or 0. So if theta isn't 90 or some multiple of 90, then the effect we're getting we're getting either no magnetic field strength or part of a magnetic field strength, or the magnetic force strength, excuse me. So that requires us to have theta equal to 90, pretty much, or no, excuse me, multiple of, it would have to be 90 or 270 or blah blah blah, right? So here I'm choosing 90, and that gives me sine theta equals 1, so I can get this full effect of the magnetic force of QVB. Here I just see that this is equal to this, and so I cancel out the Q's, which leaves us with E equals VB, and I solve for B. That's what the problem is asking for, so I just move this V under the E, so I get B equals E divided by V, little v. But we have two plates. We know the gap in between them. We know the the potential between them, the electric potential. So we're just expressing electric field strength as potential divided by distance. And if you take potential divided by distance, you actually get, coulombs force. You get the same K, Q, um, oops, get the same K, Q, Q over R squared. Because the R is D. D is what R is in this case. Oh, you guys did not see that. Well, yeah, this nice little equation here, Q1, Q2, and then over R squared. But yeah, so I said this, and then oh yeah, no problems. I just substitute from here to here, and then I plug in numbers, and that's how I get the answer. Does that clarify? I see there were like about 3 people with questions on this particular problem. Does that clear it up for everybody that had a question for this? All right, perfect. For the other people, did I clarify sufficiently your concerns, your questions? All right, great. There was somebody asking about problem 4. Let me see what that question was. If you can remind me what the question was for problem 4.
I think the question for problem 4 was about the direction that B points, or that
Oh,
BP.
okay, yeah. So actually, here's an intuitive explanation of that without really going into too much math. You have current curling this way, so the right hand rule tells us that the cross product would be the thumb, or that's where the B would point. Sorry, B would point this way if current is curling this way. So with that being said, you have this kind of half donut shape, geometry, whatever you want to call it. It's a loop, but a looped wire, current going to the wire. But these points, they don't really curl with respect to they really just go through this point. If you draw a line, through both of them, they just go through this point. So there's no magnetic field strength induced by these parts of the loop. But you're gonna get one from here, and you're gonna get one from here, right? Each of these induce their own magnetic field strengths for this point P. So, okay, this bigger loop, or this bigger arc, it curls this way. So the right hand rule tells us it should point out here. But using the right hand rule again, okay, it's pointing in the opposite direction. It's curling in the opposite direction. So that should induce a magnetic field that points in the opposite direction as what's induced from this part of the loop. So now the question of where the total, magnetic field at this point points is more of a matter of which one is stronger, because at that point this induces a magnetic field here in the form of a vector. This induces the same individually, not the same exact vector, but it induces a magnetic field vector here as well. So when we want to find the total, we just add them all up. And let's see. Actually, okay, that's someone else had a question. It turns out that loop 2, or the section 2, I guess, of this loop has the greater magnetic field strength. Or yeah, it has the greater magnitude. Right? Let me actually double check that. But whichever one ends up being the stronger magnitude is gonna determine in which direction it points. Because at that point, there's a tug of war of opposite directions, and the stronger magnitude wins that tug of war. So let me verify. So here, was this B2 minus, oh no, hold on, no. This was B1 minus B2, right? Did I? Yeah, B1 minus B2. Yeah. I did B1 minus B2, and at the end, I got a positive value from subtracting the second one from the first one, which means that the first magnetic field strength is larger, which means that, excuse my earlier mistake, this circular arc, this half arc, should induce a stronger magnitude of magnetic field strength, which means that since it's curling this way, it's gonna go into the it's gonna go into the page because of the right hand rule. Does that make sense?
Yeah, so it doesn't point at us, it points away.
Yeah, actually I should correct that. It points away from us.
Okay.
Yeah, that's when I was. Yeah, I that's a mistake from when I flipped when I had it B2 minus B1, and then I ended up with a negative value, so I just kind of flipped everything so it can be positive. But yeah, subtracting B2 from B1 gives a positive value, so B2 must be smaller. So this magnitude B1 has more authority